In this video, we are going to talk about dimensions of vector spaces. This is our overview slide, which we'll spend a few minutes going over before we go over each of these topics in more detail and with more examples. In our video about bases, which will review the definition, a basis of a vector space V is a list of vectors in V that is linearly independent and spans V. We had this theorem that said basis length does not depend on the bases. That is, any two bases of a finite dimensional vector space have the same number of vectors. And that brought us to the definition of dimension. The dimension, notated dim v, of a finite dimensional vector space is the length of any basis of the vector space. We have these two quick examples. The dimension of f of n is equal to n because the standard basis of f of n has length n. And then the dimension of the space of polynomials of degree m or less is equal to m plus 1 because the standard basis for polynomials, that is 1z squared up to zm, has length m plus 1. We have this theorem here regarding dimensions of a subspace. So if V is finite dimensional and U is a subspace of V, then the dimension of U is less than or equal to the dimension of V. And our last two theorems then are really useful. It's going to have the work that we need to do to prove that a set of vectors is a basis. The first one says, linearly independent list of the right size is a basis. So suppose we have a finite dimensional vector space V. Then every linearly independent list of vectors in V with length of dimension V is a basis for V. The example we have of this theorem is to show that 5, 7, and 4, 3 is a basis for F2. So the first thing we have is the dimension of F2 is equal to 2 because we know that F2 has the standard basis of E1, E2. So the dimension is F2. So we can either show 5, 7, 4, 3 as a basis by using this theorem here, showing that these two vectors are linearly independent, or we can use this theorem down here to show these two vectors span F2. But since we're illustrating this first theorem, we're going to show they're linearly independent. And also, this is the easiest way to prove 5, 7, 4, 3 is a basis. So two vectors should span, or two linearly independent vectors will span F2 and therefore will be a basis. And the easy thing to note is since there's only two vectors, if they are if two vectors are linearly dependent, then they will be scalar multiples of each other. That is, I've written this here. If a1 v1 plus a2 v2 equals 0 has a non-trivial solution for a1 and a2, then we can rewrite v1 as a scalar multiple of v2. And remember, the reason why it needs to be non-trivial is so that this division is not by 0. Here you can see these two vectors, 5, 7, and 4, 3, are not scalar multiples of each other, and therefore they're linearly dependent. Okay. So it's easiest to note that 5, 7, 4, 3 are linearly independent because they are not scalar multiples of each other, and therefore two linearly independent vectors will span F2 and then therefore be a basis for F2. The last theorem then is a corresponding theorem to this linearly independent list of the right size is a basis. A spanning list of the right length or right size is a basis. So suppose V is finite dimensional, then every spanning list of vectors with length dimension V is a basis of V. And that concludes our overview. So now we can go back up and take a closer look at all these examples as well as proofs of these theorems. We'll start with a quick review of our definition of a basis. So a basis of a vector space is a list of vectors that is linearly independent and spans V. So the two requirements to show that a set is a basis for a vector space are that it needs to be linearly independent and it needs to span the space. We had this theorem that said that basis length does not depend on the basis. That is, any two bases of a finite dimensional vector space have the same length. And from there, because we know from this theorem, we can define dimension. So the dimension notated dim of V of a finite dimensional vector space is the length of any basis of the vector space. That is, it's the number of vectors in the bases. Our first example is the dimension of f to the n is equal to n because the standard basis of fn has length n. And looking at the standard bases, we sometimes note that with the e1, e2 up to en vectors. And these are the vectors where, so e sub I vector has zeros everywhere except in the ith coordinate. So e1 is going to have zeros everywhere except in the first coordinate. e2 will have zeros everywhere except in the second coordinate. Up to en is going to have zeros everywhere except the nth coordinate. And you can see then there are these n standard bases vectors that will span fn. And if it helps you, you can think of this as rn, like r to the third, r3 or r4. F just means instead of real numbers, you can have complex numbers as well. We've talked about the vector space of polynomials of degree m or less. So the dimension of the polynomial space of degree m or less is equal to m plus 1 because the standard basis for the polynomial space is 1z squared up to zm. And you can see the length is the m plus 1. We have this next theorem that talks about dimensions of a subspace. If V is a finite dimensional vector space and U is a subspace of V, then the dimension of U is less than or equal to the dimension of V. Of course, the number of vectors in U is always going to be less than the number of vectors in V because U is a subset of V. However, we want to know the numbers of vectors necessary to form a basis. Is that less than or equal to the number of vectors necessary to form a basis for V? And this theorem will help us answer that question where it tells us the dimension of U is always less than or equal to the dimension of V. The two facts we're going to use is first, the basis of U must be linearly independent and it's a subset of V. And we know it's linearly independent because that's one of the requirements for a basis. Second, the basis for V must span any subset of V, that is, it spans U. And again, that's also in a requirement for the basis of V. Next, we're going to use this theorem. We had this in our video about linear independence. In a finite dimensional vector space, the length of every linearly independent list of vectors is less than or equal to the length of every spanning list of vectors. In that video about linear independence, we proved this theorem, but I'm just going to show you quickly how we used it. We had a list of 4 vectors in R3, and we wanted to show they were not linearly independent. And the way we did that is we said, well, we have 3 vectors, the standard bases that span R3, and by this theorem, every linear independent list of vectors has to be shorter than the list of spanning vectors. Since we have 3 vectors that span R3, these 4 vectors in R3 cannot be linearly independent. Getting back to our proof over here, U is going to be our set of linearly independent vectors whose length, according to this theorem then, must be less than or equal to the length of every spanning list of vectors. Since V, our basis for V, spans U, then the dimension of U must be less than or equal to the dimension of V. And I have that written here. The length of the basis for U, that's my linearly independent list mentioned in this theorem here, must be less than or equal to the length of my bases for V. That's my spanning list listed here. Therefore, the dimension of U must be less than or equal to dimension of V. Next, we have 2 theorems that will have the amount of work we need when we want to prove a set of vectors is a basis. The first one is linearly independent lists of the right size is a basis. So if V is finite dimensional, then every linearly independent list of vectors in V with length dimension V is a basis of V. And second, the spanning list of the right size is a basis. So suppose V is finite dimensional, then every spanning list of vectors with length dimension of V is a basis for V. We are going to start with our proof of the first theorem, linearly independent list with the right size is a basis. So if you have a finite dimensional vector space, then every linearly independent list of vectors in V with length dimension of V is a basis of V. We are going to start then by assuming the dimension of V equals n. That means any basis of V is going to have n vectors. So next, we're going to look at a linearly independent list of the right size. So that would be v1, v2, up to vn. We're going to assume it's linearly independent. And what we want to show is that this set of vectors is a basis. From our last video when we talked about bases, we had this theorem that said any linearly independent list can be extended to a basis. That is, every linearly independent list of vectors in a finite dimensional vector space can be extended to a basis, which means our list here of n linearly independent vectors can be extended to a basis. But we also know that the basis length does not depend on bases. In other words, the dimension is equal to n. So any basis has to have n vectors. So we can't add any more to here. If you want to think of how we extend it, well, we extend it by adding an empty list of vectors because, again, the dimension of v is equal to n. And therefore, our list of n linearly independent vectors must be a basis. And this theorem is nice because when you want to prove a set is a basis, if you can show they're linearly independent and you know what the dimension of the vector space is, once you have n linearly independent vectors, you actually don't have to go through the trouble of proving span. And that's what I mean by your work is going to be halved. In my previous video, when I discussed bases, I took pains for a number of examples to show that the set of vectors both span and were linearly independent because that was the definition of bases. But towards the end, there were a couple of examples that I did where I said, okay, now we have n linearly independent vectors. I'm not going to prove span, but I can tell you that this will be a basis, and I told you in the future you'll also know why, and I asked you to take my word for it. Or I told you you could go ahead and prove span for yourself. But this was the theorem that I was referring to, which is why at the very end I stopped proving both linear independence and bases. This next theorem is a corresponding theorem that a spanning list of the right length is a basis. Suppose V is finite dimensional, then every spanning list of vectors with length dimension V is a basis of V. We start off the proof very similarly. We say the dimension of V is equal to n, and then we have n vectors that span our space V. So this is our candidate set for our bases. And from our previous video on bases, we had this theorem: a spanning list contains a basis. Every spanning list in a vector space can be reduced to a basis of the vector space. So remember, for the spanning list, to make it into a basis, we threw out any vectors that were linearly dependent on the remaining list of vectors. So here, either our candidate list of v1, v2 up to vn is a basis, or it can be reduced to a basis. But using our theorem again, that basis length does not depend on a basis, v1, v2 up to vn cannot be reduced to a basis since the dimension of v is equal to n, and therefore our n vectors that span the space is a basis for v. These two theorems now will give us an easier way of proving a list of vectors is a basis as long as the number of vectors in your list is equal to the dimension of the vector space you're trying to show a basis for. You only need to prove then linear independence or spanning. You don't have to prove both if the list of vectors is the right size being equal to the dimension of v. Our first example is to show the vectors 5, 7, and 4, 3 is a basis for f2. And the first thing to note is the dimension of f2 is equal to 2. And that's because we can always use the standard bases, that is our 0, 1 and 1, 0 is a basis for f2. So we know the dimension is equal to f2. From our two theorems then, which I have here for your reference, the first one saying linearly independent lists of the right size is a basis and spanning lists of the right length is a basis, we can either show that our two vectors 5, 7, 4, 3 are linearly independent, or we can show that they span f2. And in this case, because there's only two vectors, it's easy to show that they are linearly independent because remember, two vectors, if they're linearly dependent, That means there's a non-trivial solution to a1 v1 plus a2 v2 equals 0, which means we can solve for v1 is equal to a2 over a1 v2. In other words, one vector or both vectors are scalar multiples of the other. Since we can see 5, 7 is not a scalar multiple of 4, 3, they are linearly independent. And now we apply this theorem here, linearly independent list of the right size meaning length of the bases, is also a basis. So that means 5, 7, 4, 3 is a basis. Our next example is to show the vectors 1, x minus 5 squared, and x minus 5 cubed is a basis of the subspace U of polynomials of degree 3 or less, defined by U is equal to the polynomials in the polynomial space of degree 3 or less, such that the derivative, the first derivative of the polynomial evaluated at 5 is equal to 0. To get kind of a feel for what this space looks like, that's the subset or subspace U, we're going to take the first derivative of our first vector 1, which is equal to 0. So that qualifies for U because p prime at 5 is equal to 0. We'll take the first derivative of our second vector. So the first derivative of x minus 5 squared is equal to 2x minus 5 evaluated at 5. We see that's equal to 0. And then the first derivative of our last vector, x minus 5 cubed, is equal to 3x minus 5 squared. We evaluate it at 5, and we get 0. And again, I just did that to get a feel for what the space looks like. I also want to note that the dimension of the polynomial space of degree 3 or less over R is equal to 4. Remember, the standard basis for this space is 1x, x squared, x cubed. Since U we're proposing is a subspace of P of 3, that means the dimension of U has to be less than or equal to 4. And since U is a proper subset, in other words, you can see here the description of U, there are many other polynomials of degree 3 or less. So U does not span the whole space of P3. So since U is a proper subset, we know that the dimension of U must be less than or equal to 3. For this problem, I want to be illustrating one of these two theorems, one with a linearly independent list of vectors, or the other with a list of vectors that span. For this subset U, I feel like it's easier to do linear independence because I'm not sure exactly how to express the span of this set U. There's no real standard basis for U. So let's do linear independence. I'm going to take scalars, multiply them by each of my vectors 1, x minus 5 squared, and x minus 5 cubed, and then I add those terms together and I set them equal to 0. I expand this out just doing the algebra here. I group my coefficients, I group my coefficients in front of x, I group my coefficients in front of x squared, and I group my coefficient in front of x cubed. And what that gives me right here is that a3 must equal to 0, which means this coefficient here has to equal to 0, which means a2 equals 0. Looking over here, we have the same thing, a2, a3 are both 0. Here, since a2 and a3 are 0, that must mean a1 must equal to 0. So all of the coefficients are equal to 0, which means there's only the homogeneous equations, and therefore the three vectors, 1, x minus 5 squared, and x minus 5 cubed, are linearly independent. One more thing to note, now that we have three linearly independent vectors in our space U, that means our dimension of U has to be at least equal to 3. So what we have from this previous statement, dimension of U is less than or equal to 3, and now we know dimension of U has to at least equal to 3 to accommodate our three linearly independent vectors. We know that the dimension of U is equal to 3. Now we can use this theorem here about linearly independent list of the right sizes of bases. And I'm going to copy this theorem down here for reference. And the theorem says, suppose V is finite dimensional. In this case, our vector space V is the space U, the one where the derivative evaluated at 5 equals 0. So remember, the vector space is U. then every linearly independent list of vectors, and here we have our three vectors, 1, x minus 5 squared, x minus 5 cubed. We showed these are in our vector space U, and they're linearly independent. With length dimension of our vector space, and remember the dimension of U we found is equal to 3, and the length of our list of vectors, our independent vectors, is 3, so that makes this list of linearly independent vectors a basis for U, and we're done with our problem. And then we have the second theorem that's going to reduce the work of proving a list of vectors is a basis, and that is the spanning list of the right length or right size is a basis. So suppose V is a finite dimensional vector space, then every spanning list of vectors with length equal to dimension of V is a basis of V. To review what we have covered in this video, we talked about dimension of a vector space. We started by reviewing the idea of a basis of a vector space, and that's a list of vectors in the vector space that is linearly independent and spans V. We had this theorem that says basis length does not depend on the bases. In other words, any two bases of a finite dimensional vector space have the same length or the same number of vectors in them, which leads us to the definition of dimension. The dimension of a vector space, noted dim of V, of a finite dimensional vector space is the length of any basis of the vector space. So our examples include dimension of Fn is equal to n because the standard basis of Fn, that is E1, E2 up to En, has length n. The second example we have is the dimension of polynomials of degree m or less is equal to m plus 1 because the standard basis for polynomials of degree m or less is equal to 1z squared up to z to the m, which has length m plus 1. We have this theorem regarding the dimension of a subspace. So if V is a finite dimensional vector space and U is a subspace of V, then the dimension of U must be less than or equal to the dimension of V. Next, we have our two theorems that reduces the work of showing a list of vectors is a basis, and it depends on having a list of the right size, a list of vectors of the right length, the right size. And the right length, the right size is equal to the dimension of V. So our first theorem, which is linearly independent list of the right size, is a basis. So suppose V is a finite dimensional vector space, then every linearly independent list of vectors in V with length equal to dimension of V is a basis of V. Our second example is the spanning list of the right length is a basis. So suppose V is a finite dimensional vector space, then every spanning list of vectors with length equal to dimension of V is a basis of V. And our example was of this first theorem here to show that 5, 7, and 4, 3 is a basis for F2. Now we know since F2 has the standard basis E1, E2, dimension of F2 must be equal to 2. So we can either show that 5, 7, and 4, 3 is linearly independent and then use this theorem here to say two linearly independent vectors will span a vector space F2 which has dimension 2, or we can show 5, 7, 4, 3 span F3 and then use this theorem here that says we have two spanning vectors, the number of vectors is 2, which is equal to the dimension of V, so therefore 5, 7, and 4, 3 is a basis. For this problem, it's easier to use linearly independent. And it's easy to note that 5, 7, and 4, 3 are linearly independent because they are not scalar multiples of each other, and therefore 5, 7, 4, 3 is a basis. And that is it for this video. Thank you for watching.